Hi and welcome everybody. Sorry, I had a few difficulties with my audio setup, but now I'm here. Hi and welcome back everybody. Today I'm going to continue on my project of hooking up my doorbell to MQTT and SIP. I don't know if you watched the stream yesterday or watched the recording, but what we did yesterday was we reverse engineered this door microphone loudspeaker module. So we picked it apart, and here you can see the PCB and the microphone loudspeaker. And we found out that basically the loudspeaker is just directly hooked up to the terminals here. The loudspeaker is directly hooked up to the terminals here, giving you a better view of everything. So here you can see that this is the PCB with the loudspeaker and the microphone, and here you see the terminal block. So we found out that the loudspeaker is hooked up directly to the terminal block, and the connectors 9 and 12 here, and that the microphone has this amplifier circuitry here. What this amplifier circuitry does is that it modulates the sound waves on the current that this amplifier circuit draws. So what we did yesterday was we hooked up the oscilloscope, and we were able to see the sound waves from the microphone, because I have here a shunt resistor which allowed me to measure the current with the oscilloscope going into this device. And I set the oscilloscope to AC coupling, which filtered out the DC part, which was the base current this module draws. And with that we just saw the sound waves. I then played a sine wave form on my cell phone and put it close to the microphone, and we were able to see the sound wave. What we are going to do today is we're going to take a look at this module here. This module here is the indoor part of this setup, which was sitting in between of this device over here and the PCB. So basically this device was hooked up to this device, which was connected to power, and on this terminal side here it was connected to the PBX. Sorry, I said PCB. Okay, again, this is the loudspeaker model sitting outside. This was inside in the wiring closet and was connected to the PBX. As I told yesterday, this is not a simple analog telephony interface. So it's not just an FXO interface, it's a proprietary interface which PBX systems used back at the time. This whole piece of electronics here is 18 years old. And so that's that. Today I'm going to open this up and look at what's inside to determine if I can use that for my planned project or if not. So the plan is to hook this up to SIP, either via a Raspberry Pi and a small USB sound card, or via this device here, which is designed for public address systems. I'm going to wait a few more minutes to see if some more people start. As always, you can just pop in any questions you have into the chat. And yeah, that's currently the plan. So I'm just going to wait like 2 or 3 more minutes, and then I'm going to start with today's show. Feel free to say hi when you're watching. Like to know who is watching, and just tell me a bit about yourself, like who you are and why you are watching this. Hoo-hoo. Hi, Franzi. So I have to give a bit of a credit because what actually the person who inspired me to do this is Scanline. If you don't know her, check her out. She's absolutely awesome. She is an engineer from the States, and she builds epic things. Check out her channel if you don't know her. I can only recommend. Actually, I hope I can go the way and hook it up to the Raspberry Pi, because it's just way more fun. I can do whatever I want with the thing then back later, because I just can code tons of stuff for it. And yeah, and also I have the GPIO pins in the Raspberry. I can hook it up to the door lock, and also to the of course then to the doorbell buttons. And as it's planned, all the events like doorbell, rang and stuff will be broadcasted to over MQTT, and I already wrote a small client in Python which displays messages on my computers via libnotify. I'm going to write a client in Qt for Windows, because there are here a few Windows machines in the house. And yeah, it's going to be fun. I think we give it 2 more minutes and then I'm going to start. Okay, I think we have waited long enough. As the video count didn't go up, I'm not going to repeat the whole intro and what I'm going to do. I'm going just to start doing it. So, going to open up this device here now. And we are going to take a look what's inside. Okay, there's a lot inside actually. Way more than I expected to be inside here. That's surprising. So yeah, that's quite a bit of something in here. Let's see. I think it goes apart like this. Yeah. So just going to take this apart. And that should come out now, if I see that correctly. Yes. So, don't fall on the floor. So now here we got that thing. Interestingly enough, there are a lot of transformers on here. So here we have a relay. I'm sorry. So here we have a relay. Guess that's most likely designed to operate the door lock. Here we have an operational amplifier. If I'm not mistaken, let me Google that for you quickly. It's an LM324N, and I'm pretty sure this is an operational amplifier. Yeah, it's a quad operational amplifier. And here we have this thingies. Are basically look like transducers, but I'm not 100% sure. Also, we have here these two blocks up here on this second PCB, and I guess they are transducers too. They're called U1 and U2. I don't know. They have actually they are actually labeled. You can't really quite see that, but that's a German Ü. That's not a U, it's a Ü. It's a German letter. So guess that's something I haven't seen yet on electronic parts. That's interesting. So let's see if we find some documentation for this device. Oh, this is even certified by the German Telecom and the Austrian Telecom. You see here, these are certification numbers. That's interesting. So let's see and if we can find some documentation of this device. But as it's so old, it could be that that we don't find anything anymore. No, actually it's still online. So here we have the device. Let's look up the product information. Okay. Doesn't help us much because we still don't have any information what all of these connectors do actually. Let's see. Wait a second. I don't remember yesterday, but yesterday I looked up the schematics for this loudspeaker microphone module, and we've discovered that they didn't add up. But here we now have, for a little bit differently labeled module, a circuit diagram, and it actually looks way more like what we discovered, because it has like the 4 transistors as to the 2 transistors in the other circuit diagram. So it could be that this is actually one of the devices we are looking for. But the funny thing is, like, they have like for lots of other random devices circuit diagrams in here, but not for this device itself, which doesn't make sense. So What the heck? I'm trying to find out what's exactly this connection is called to see if we can find some documentation on this type of connection. So that's interesting. So I found something. That's from some other company, but it looks like we now found the definition of this interface. Apparently, it's called FTSet13123D12. Whatever. You can Google that. Oh, we have an actual Wikipedia article on it. So it's only in German, but I'm going to translate it quickly. The FTSet123D12 is in Germany a common interface for PBXs to be connected to door intercom systems. Originally controlled by the Fernmeldetechnische Zentralamt, it's basically the telecommunication office or whatever. So apparently it's just a normal AB connection, just like what you got, a normal AB analog telephony connection with two potential free relay contacts. one for one to activate the door opener, and one for other thingies, and the door opener is triggered through the impulse dialing. Okay, that's strange, because if you look at this other documentation over here, basically you have this exactly the same wiring as in the Seedler thingy, and you got the TU contacts, which are opening, very surely opening the door, and the TS contacts, which are contacts that activate the door intercom system. So that's interesting. Let's look over here at this reference. Oh, it looks like, yeah. Basically, we have that looks right. We have the AB wires for the voice signal, just like normal telephony systems, and then we have the two contact closure contacts, which activate the door opener, and the other one activates the whole intercom system. So that's interesting. It actually makes things more complicated. So basically, this device actually would make it harder for us to interface everything with a Raspberry Pi or the GNOME PH1, because then we have to deal with the whole AB thing and how that works. So I'm going to put this device back together, and just as I thought I'm most likely going to do, basically design my own indoor device which hooks up to this. Going to put this back together and basically design my own device which hooks up to here, and yeah, so I'm going to put this back together, and then we're going to start and design a device to be interfaced with this. And as we've seen in the other document, we have to take another look, because apparently there are multiple versions of this device, and it could be that in this version the loudspeaker is not directly connected to these terminals. So we have to take a closer look at this PCB, and maybe even, or maybe I'm going to have to even reverse engineer it completely, like the whole circuits, but that's fairly easily done, as it's just a single layer PCB. Before we're going to do that, we just look into it. But it really looks like if this actually isn't built-in amplifier for the loudspeaker here, because we have the second potentiometer and the 2 additional transistors, so that could easily be the case here. So now let's see, this is the bottom part, and this goes should go easily. Yeah, okay, that's done. And then we have to add those spacers. Then everything goes back together, hopefully without too much effort. That's the wrong way around. So, number 1, number 2, number 3, and number 4. So, let's put this back together. Wait. Oh, okay. I was confused for a moment, but everything is fine. So yeah, okay. So, yeah, let's take a look over here. So that over here is the loudspeaker connector. Yeah, and it's definitely not hooked up directly as in the circuit diagram we saw of this device. I can pull it up again. Just give me a sec. So this is what the circuit diagram looks for this device, and yeah, it's definitely not like this. let's look over here because we saw the other circuit diagram. Going to make it a bit larger so that you can see it better. Actually no, that can also not be because the additional LEDs are missing, so even though it looks fairly close to what we've got, very close. No, that's interesting. No, it doesn't have the 14 and the 3 and everything, so no. Well, so guess we have to reverse how the loudspeaker is hooked up to everything here. Let's see. So this is the terminal for the loudspeaker. Oh, sorry, that's the microphone. I'm stupid. How did I mix it up right now? Okay, let's take a look again. So here we have the loudspeaker, and one is hooked up to this plane here, which most likely is a ground plane, but I can't be exactly sure. We have to trace the connections, but sort of, yeah, it's the ground plane, so that's wait, what? This is most likely connected to the connector number 9. which looks like it's, yes, indeed, is the ground plane. And I just noticed that I didn't know why I didn't notice that yesterday, but in the documentation you have a connector 12 and 13 for the speaker. If you look over here, there is no 13. So that means that only 12 is hooked up to the speaker, which makes things interesting. So basically we have to find out what kind of signal this PCB expects for the speaker, and we have to find out if we can use this as this, or if we have to work around that and, for example, like just shorten the whole amplifier circuitry out or so for this speaker. So let's take a look. So this is the speaker. One is directly connected to ground. The other thing goes over here, and I think this part here is a transistor. Yes, it is a transistor. So let's see how this is all hooked up. Yeah, looks like the way to go is that I'm going to get a piece of paper, and then I'm going just to start drawing and reversing the circuit diagram. And just quickly take a look at it. It's not that many parts. It looks like it's only the few caps here and the trimmer and these two transistors. So, and the few SMD resistors over here. So should be a fairly easy diagram to draw. Back in a sec, just have to get a piece of paper. Oh, whoops. I muted the microphone. I'm so sorry. Yeah, I'm going to go over all of that quickly again. Sorry for that. Yeah, things you learn while learning how to stream about electronics. So let's put that away. Take another pencil, which is nice and sharp. So, okay, what I said is, we have here the speaker. Speaker is connected to the ground plane and to a transistor and a resistor. I talked about that the transistor has three connections: collector, base, emitter, and that's how it actually sits in here or in here. And if I turn that around, we have collector, base, emitter, and the loudspeaker is connected directly to the collector and via a resistor to the base of the transistor. So now I'm going to put our transistor over here, and I'm going to in a sec look if it's an NPN or PNP transistor. And actually the base of that well, we're going to run out of space. I have to redraw that. Sorry about that. So let's draw this up nice and big, so that we have enough space for everything, because it looks like we are going to need it. Because here now comes a capacitor, and from that capacitor we go over to potentiometer, which in turn then is connected like this. And from this side we have a small cap going over here to the ground plane, and then comes another resistor, so let's try to see what actually the values are while we are going there, so that we have not such much of a hard time afterwards. That's very difficult to read. Actually can't be sure if it's 0 or 3. Let's go with a 0 for the start, because it seems more likely. So how letterings on SMD resistors work is the first two numbers are the significant digits, and the third number is a multiplier telling you the power of 10 to which the two significant digits must be multiplied. So 22 with an 223 means we have a significant number of 22 with 10 multiplied by 10 times the power of 3, so that's 22 kilo ohms over here, the top one. The capacitor is not labeled, which is pretty usual for SMD caps in this size. Oh, sorry, that's not the SMD cap. I was on the wrong place. We have a capacitor. And trying to find the multiple numbers are written on it, so that's this one over here. We leave it for now. I'm not quite sure what it is. The trimmer over here has written 2K5 on it, so it's 2.5 kilo ohms trimmer. And from the trimmer over here, we go to another resistor. Which, wait, what? Oh yeah, 221, so that's 220 ohms. And then the wiring continues, and here it gets interesting. Here it gets really interesting. So I have to think how to draw this so that we don't get into difficulties later. Let me what? Okay, let's draw it like this. I hope this works out as planned. There are actually now 3 transistors connected at this intersection. And 2 of them are hooked up in parallel, and have 330 ohms. Each. And these are hooked up in parallel. And then continue to the pin, to the plus pin. So that's started nicely. That's the plus pin. And here we have the other resistor. It's 270 ohms. It's got a bit difficult at that point. So, okay. It looks like this. Here is most likely terminal 12. There's a 0 ohm jumper resistor actually on the PCB in here, basically like in here, but I just skipped it in the diagram because it doesn't really matter. I can put it in just for reference. So here we have a 0 ohm jumper. It's just used to cross another trace in the PCB because it's a single layer PCB and they don't have any other way to cross traces. Which actually in fact is pretty amazing that like this whole PCB has only one jumper resistor. They managed to made it entirely on a single-sided PCB. So let's trace the connections further. So this goes over to cap, but we have to space it out a bit because we're going to add a transistor and everything. Also, right in a second. And actually, what's really interesting is it goes to electrolytic capacitor. Which is interesting. So it connects the trace from here, actually connects to the minus, the negative pole of the electrolytic capacitor. And then continues to the transistor emitter. So wait a second, or what it's let's just check what kind of transistors we have over here, so that we don't mix up stuff. They're quite dirty and a bit difficult to read. Okay, they are BC327s. If my mind doesn't trick me, these are NPN transistors. Let's pull up a data sheet. No, actually PNP transistors. Here we have the data sheet. So that's interesting. But now we know that, so we can actually draw them correctly. So I said that was hooked up to the emitter of that transistor. Yeah. So here we've got one transistor, here we've got the other one, and that's BC33, oh sorry, BC327. BC327. But it's of course a bit more difficult, everything, and this side over here I have to do that differently. So the trace after the 270 ohms resistor, it's also connected to the base of this transistor. And the emitter wait a second. Wait, what? Yeah. And the emitter is also connected to the plus pole. And the base the collector of the transistor goes through a 12 ohm resistor all the way back to the emitter of the resistor up here. So basically this wire over here Goes all the way up. Passes through a here. And to make things more interesting, there's actually 2 more capacitors hooked up to the ground plane. 2 more electrolytic capacitors with 100 microfarads and 16 volts. So we've got 2 more electrolytic caps. Which are connected to the ground plane, and both of these are 100 microfarads and 16 volts. 100 microfarads and 16 volts. The other capacitor, see if I can read that. The other capacitor over here has 22 microfarads and 35 volts. So so there we have it. That's the complete circuit diagram of the PCB in what's related to a loudspeaker. I'm going to try to find out now this one cap over here. Going to try to find out with a bit of googling what's that it? What kind of capacity it has. So I found something on eBay which basically looks quite similar to that, has the same labeling, and as it turns out it's an 0.68 microfarads 63 volts capacitor. Let's check that on Google again. Yeah, seems like it is actually correct. If we look at all the other results here for Google. So yeah, that capacitor, which is connected in between this one here, that's 0.68 microfarads and 63 volts. And this cap over here is the small SMD capacitor, and we don't know what kind of capacity that has. So see that it's all nice and clean over here, the circuit diagram, and then I'm going to hold it into the camera so that you can take a better look at it. Yeah, so let's see if you can make that viewable better for you on the stream. Actually pull out a bit here. So, and yeah, so here it is. That's basically a circuit diagram of this PCB in relation to the loudspeaker. So let's take a look at this. I have to say that's a bit surprising. Trying to figure out how this circuit actually works. So here is the plus connector. The plus connector is actually hooked up to the DC power supply of 8.3 volts. So this 8.3 volts is here are resistors, which are actually 165 ohms, because there are two 330 ohms resistors in parallel, and through this resistor it's directly hooked up to the input, and there is no cap or anything isolating it from DC, which already is interesting. And then we've got this part here. So so you basically, we have this PNP transistor here. With this feedback circuitry, so I'm really shitty at analog electronics, so that's not so easy for me to figure out what's going on here. Give me microcontrollers, then I'm happy. Analog electronics sucks. I hated it at school also all the time. It could be that they again designed it in a way so that this audio signal is transmitted via a current loop. Should if would make sense for these two big resistors over here. So that on the other side basically there's just a current sink which is driven by an audio signal, and it varies. Whereas the amount of current it draws, and this in turn is then turned into the audio waveform. And looking at this, it seems like that could be the way it's actually done. Let's see what would happen if I would just short circuit here this. So we imagine that that's hooked up to ground. We would have a voltage drop of 8.3 volts across these two resistors. So we have a voltage drop of 8.3 volts. This cap here is slowly charged to 8.3 volts via this resistor over here, and then we have, which would turn on this resistor, which would point 8.3 volts over here with these two caps storing this 8.3 volts. And the 8.3 volts get over here. And now we have to look at here. So let's now say that this potentiometer is just pointed over to here 100%. So this is a short circuit, we can ignore it. This is 220 ohms resistor towards ground, and we have this cap here. So what would happen is, for a brief amount of time, this transistor would turn on until this cap is loaded. As it's very small, this would not take very long. So this transistor would, basically what this here does is in combined with this trimmer, you can control the gain of this transistor. So let's say this is floating. What's going on then? Then what's going to happen is this. We have here 8.3 volts. And we have to see where the next ground is. So this is not connected to ground, so we have a connection to ground over this capacitor, which is not really counts because it charges up quickly and then it's floating again. So letting that input float actually would do not really anything. So let's see. This is short circuits, not like completely short circuits. That would make a difference. I'm actually thinking about ending the stream for today, and I'm basically going to figure out how this circuit works, and if everything goes right, I'm going to stream again tomorrow, and then I will be able to tell you how this circuit works, and then we can get to the more interesting part of actually hooking this up to the Raspberry Pi and getting all of that to run. I think it's now not very interesting for you if you just watch me sitting here and trying to figure out how this thing actually works. So thanks for watching. I hope it was interesting for you. I know it's going a bit slow right now because of the whole reverse engineering part, but maybe it's interesting to watch the process of actually reverse engineering something like this. And see you tomorrow, and thanks for watching. Actually, if you want, follow me on Twitter. Going to post the link to the video also there later. My Twitter profile is linked in my channel. And if you want to help to make the stream better, I have an Amazon wishlist with gear to make the stream better. I'm going to post it later on Twitter. So yeah, thanks for watching and have a lovely evening. Goodbye.